And these computing elements are pretty abstract elements, basically black boxes. You have a black box that performs addition and a black box that performs multiplication or integration, and you don't have to think about their inner workings.
Black boxes, abstract elements. What Bernd Ulmann, one of my guests for this episode, is talking about is a special kind of computer, the analog computer. And together with him and Daniel Thuerck, we're going to find out what they are, how they work, and all the wonderful things you can do with them. When we think of computers, we usually think of digital devices, and in particular, devices that follow the so-called von Neumann architecture and design. Which sounds very fancy, but what it boils down to is a device that has an input facility, a central processing unit or CPU, where commands are being handled, a memory unit where results and commands are stored, and of course, an output. Okay, modern computers have a lot more stuff in them, but in essence that's what you find in most of the devices we're all surrounded by these days, be that your mobile phone or your laptop. And over the decades, we developed sophisticated techniques to manipulate and operate these devices, not least the whole range of programming languages that help us feed instructions to these computers. But these are not the only computing devices we have, and in this episode I want to shine a light on one type of computer that follows very different principles, a class of computer that isn't even digital. A type of machine that's called an analog computer. Depending on how you define a computer or calculator, analog devices have existed for a very long time. For sure, they predate the digital era. One of the simplest ones, according to Wikipedia, is the slide ruler. I just missed out on learning how to use them at school, as our class was the first to introduce an electronic calculator, the now iconic TI-30 from the US company Texas Instruments. But my dad used slide rulers extensively at work as a civil engineer in the 1960s, and I remember we actually had one at home. But there are far more sophisticated analog computers, mechanical, hydraulic, and of course electronic. In search of some examples, I made my way to the Science Museum in London, late 25, which has a fine collection. And in fact, when you go up the floor to the Winton Gallery, where you find the sections on mathematics and information technologies, you're greeted by a machine of a unique, if unfinished kind, the Difference Engine by Charles Babbage. But I was actually in search of another kind of analog computer, one that is neither entirely mechanical like the machine from Babbage, nor based on electronics. And then I found it just a few steps into the gallery. So I'm standing here in front of the machine designed by Bill Phillips, a guy from New Zealand who in the 1940s and the late 1940s designed an analog computer, but not an analog computer like you might imagine. It's an analog computer that is using water fluid dynamics to show how the economy works in a country like the United Kingdom. It was something that was finished in 1949 and shown at the London School of Economics. And it's quite a contraption because you can see there's a water tank and then the water is pumped upwards to see how money flows after taxes, savings, consumption, expenditure, etc., and government spending. So it's quite interesting. It's not electronic, as I said. It's entirely based on fluids and mechanics. The Science Museum has a few other types of computers, electronic mostly, and it's worthwhile checking them out if you're there. But the question that puzzled me was, are analog computers a thing of the past? Can they only be found in museums these days as a sign of a bygone era? Or is there still a space, or perhaps even a need for them today? Trying to answer all of these questions brought me quickly to my guests for this episode, Bernd Ulmann and Daniel Thuerck. Both are scientists, engineers, and, as you will no doubt hear, enthusiasts of all things analog computers, because both believe that the best days of analog computing still lie ahead. So over to them now.
I'm Bernd. Analog computers are my passion since I'm about 14 years old. So I'm doing this now for 40 years. And basically, analog computers are what brought me eventually to studying mathematics and then philosophy. And I also wrote my PhD thesis on analog computers. So that is my idea fix in life, doing analog computation.
Okay. Daniel.
Hi, Peter. Nice to be here, and thanks for giving us the opportunity. So I'm Daniel. I come from, let's say, the dark side, as Bernd would put it. I come from the digital side. I'm a computer scientist by training. I think I started programming when I was 9 years old in some version of BASIC because I wanted to do my own computer games. I became bored of the games that were available. And then I ended up doing computer science at university, did my PhD mostly about linear algebra on GPUs, and spent some time in the States working as a computer scientist. And then I joined Anna-Britt about 1.5 years ago and also started doing analog computing.
Just to warm us up a little bit, when we think about computing or in computers, we think about the machines we're sitting right in front of. Digital machines, laptops, personal computers, what have you, something digital. So what is an analog computer then?
An analog computer works on a completely different foundation. A digital computer, as we are used to them, executes an algorithm. So it executes individual simple instructions step by step. An analog computer, on the other hand, is based on, and that is where the word comes from, on an analog, on a model. So a quantum computer, for example, also is an analog computer since it relies on a quantum mechanical model of some problem. And the analog computers we are interested in, they use electronic models for problems. So if you want to solve a problem, you think, can I set up an electronic model that has the same underlying mathematics and then perform a measurement on this model? So the advantage is you have 100% parallelism. You let physics do the computation. There are no individual instructions. There's no sequential execution. And you have an incredible high energy efficiency. So it's all about model-based computing.
We're talking about electronic analog computers, but there are actually quite a number of mechanical ones. And I went to the Science Museum in London recently, and I saw, I think, a part of the Babbage differentiator, I think, and other ones. But electronic analog computers is what you're looking at the moment, isn't it?
Yeah, exactly. There were in the past a lot of mechanical analog computers, even well into the 1970s in some avionics systems, for example, because mechanics is just very robust, especially in times like the Cold War when you fear an electromagnetic pulse. And you had analog mechanical computers for tide predictions. You had large-scale differential analyzers in the 1920s, 1930s, which solved intricate differential equations by purely mechanical means. So an analog computer, like a digital computer, does not really depend on the substrate, so to say. You can also build mechanical digital computer. Babbage analytical engine, if it would have worked, would have been a completely digital computer, albeit in a mechanical implementation.
That's true. But let's go back to the electronic analog computers, because that fascinates me. How can you build an analog with an electronic circuit? If you can give simple examples like addition, for instance.
Yeah, addition is surely the most simple problem you can solve electronically. If you remember Kirchhoff's law from physics lecture, then you have currents flowing through resistors. And when you tie several resistors together at a common summing junction, all the currents will add up at the summing junction. So there you have it, an addition with just a couple of resistors. And even something which looks much more intricate, like an integration operation, is equally simple since you can just charge a capacitor. And you can perform addition and integration really easily with a handful of discrete electronic components in an analog computer.
Daniel, you wanted to say something?
When we talk to people and explain analog computing, we sometimes use an even simple metaphor that is not based on electronics, but just imagine a river of water, maybe the Thames in London, right? It's just flowing. It's a natural phenomenon. That is basically an analog system. You have some locks. You have some like boats, etc. You can change the locks, you can open some locks, but the river is flowing nevertheless. Whereas in a digital computer, it's not really a river. It's a sequence of pools, and you have to carry water from the first pool to the second, to the second, to the third. So it's not a process that runs by itself. It really is a sequence of steps that you have to undergo, or the machine have to undergo. And that is also an analog, by the way. So if I have two rivers that are joining to a bigger river, that's essentially addition. That's the analog of what happens in the electronic system.
It's funny you mentioned water and water flow down the river, because one of the exhibits at the Science Museum in London was actually a hydromechanical computer, if you like, which is, I think, an economic model by Philips.
Yeah,
By Philips, exactly.
By Philips, the financephallograph, which even found its way into literature due to Terry Pratchett in Making Money. There, the machine was also mentioned.
Indeed, yeah. It is quite a contraption, actually. I went to see that, and it is a very intuitive and very visual calculator in a way. So, but it's fascinating. But what I'm taking away from this is, in order to come up with this analog in electronics, if we stay with electronics now, you actually have to build the wiring and the connection between all the different components in order to do that, no?
Yeah, but I would be more happy with the phrasing, you have to configure the connections. In a classic analog computer, you actually had to plug in hundreds or sometimes thousands of so-called patch cables to connect the various computing elements. And these computing elements are pretty abstract elements, basically black boxes. You have a black box that performs addition and a black box that performs multiplication or integration, and you don't have to think about their inner workings. And in a classical system, you then used individual cables to connect the various inputs and outputs of the computing elements. That obviously does not scale. So what we are working on are reconfigurable analog computers, where a digital computer basically controls which analog computing elements are connected to which other analog computing elements. But you are right, fundamentally, but it should be reconfigurable.
Okay, and I think we're going to come to that. Well, we're going to come to that right now, because what does this wiring, this abstract wiring or configuration, as you call it, then look like? In programming on digital computers, we're used to programming languages like Python or C or C++ or whatever. But how does this work then on an analog computer?
I think Bernd already put it best to describe how it's programmed on a low level. Usually liken it to the stack on a digital computer. In the first time of the digital computer, people used assembly or even punch cards, right? But let's stay with assembly. It's very low level. You describe each individual step of the computation. You load two numbers from the memory, you add them, and you put them back into memory. So it's like a step-by-step instruction of what happens. Yeah. Whereas in an analog computer, like Bernd put it, you're already given a bunch of compute elements. One compute element could be an integrator, one could be an adder, one could be a multiplier. And then you define signals, and then you connect these individual elements to define these signals. So for example, if I were to multiply two numbers, I'll take two inputs, so input sockets on analog computer, connect them. So in the old world, you would just use two patch cables to an adder element. And then the output of the adder will be the sum of the two input signals. But in an analog computer, we don't have memory, right? So its data is flowing, basically. If I have two input signals, the addition is performed instantaneous. And that is very much on the lowest level of programming on an analog computer. But as you can imagine, as problems become larger, like Bernd said, we are also working on scaling analog computers. At some point, it becomes infeasible to provide all these connections by hand. Even on one of our smallest devices, the LuciDuck, which has 32 parameters, so 32 numbers I can set, and it has 12 computing elements. That's already a challenge if you do it manually, and you need to keep all these connections in your head, because you can basically connect any element to any element. So we've already started working on it. We built a compiler. Like Bernd said, the main principle behind analog computing is the analogon, so the building the model. And there's different paradigms in science to build these models. One is, for example, differential equations.
Right.
You are a physicist, right? So you are more than familiar with differential equations, I imagine.
I might be a little bit rusty by now, but
exactly.
Moving on.
And as long as your differential equations limit themselves to multiplication, additions, integrations, then there's an almost one-to-one correspondence between the differential equation and the configuration of the analog computer. So in the differential equation, we multiply numbers, for example. So we just take these two numbers, connect them to a multiplier. And then we do this recursively, and we end up with what almost looks like a configuration of the analog device. Of course, there are several specialties of the hardware. Like there's a certain structure you need to follow. The coefficients can only have a limited precision, and all of that is taken into the compiler. So I'd say we are almost at the point where we are close to the digital computing stack, where we have on the lowest level just a netlist that defines the connection between the elements on almost the hardware level. On the highest stack, we have ODEs, so differential equations, that can be entered by any language, Python, MATLAB, you name it. This whole stack runs automatically. Essentially, we are at the point now where you just enter a system of ODEs, you press a button, it takes a few seconds, and the analog computer is configured to run your model. And all the difficulties are abstracted away.
You mentioned ODEs. Sorry, what is that?
Ordinary differential equations. Sorry, I should mention that. So it's a differential equation. It's a model that only depends on the time. So there's no spatial component, meaning it's basically one-dimensional equation.
I'm with you. So I talked to somebody recently about FPGAs and that they can be configured. I mean, they're digital devices, so they're not analog devices, but they're digital devices. But they have a hardware language, configuration language, HDL. You mentioned that you can program, or you're close to being able to program an analog computer, electronic analog computer, with languages like Python and C++. So the abstraction between that, which is sort of the standard programming language, and the configuration of the analog computer, is there's a kind of a middle step that looks a little bit like HDL or VHDL that does actually the translation, if you like, from what you do in Python to the configuration of the device.
Yes, there is, as in almost all compilers, you have what's called intermediate representation. So it's a representation that is intermediate in the sense that it's between the high-level representation, which would be the model, and the low-level netlist. And if you look at it, it almost looks like assembly. So there's no load, obviously, there's no store instruction, but there's instructions such as multiply two values, add up two values. But the main difference is that there can be feedback loops. So in a digital system, time only goes forward. I load values, I process them, I store them. In an analog device, I can connect the output of a compute element to its input. And that's how I model these differential equations, for example. And that breaks almost all of the assumptions of compilers in the digital world. That's why we shipped our own. Now we are basing it on open standards, but that's the gist of it. Think of it a little bit like programming a low-level digital computer, but time flows in both directions.
So we talked about what goes into the analog computer and how you configure it, but what comes out is also quite interesting, isn't it? How do you capture, since there's no memory, basically it's real time, if you like, in a way. So how do you capture that, and how can you then use the output? I guess that depends a little bit on the computer.
Typically, you represent your values within an analog computer as voltages or as currents. And the jump from the analog domain to the digital domain can be easily done using analog digital converters and vice versa. Sometimes you want to have a close interplay between the digital and the analog computer. So you also have cases where the digital computer wants to introduce values into an analog computation by means of digital analog converters. So basically, you can use technology known from the audio equipment. You have analog digital converters and you have digital analog converters to bridge the gap between both representations.
I think we're now coming to the point where we understand, hopefully, a little bit how analog computers work, electronic analog computers. I would like to move to the application of them. Where would you find them, and what are the kind of use cases where you see analog computers today?
is an incredible amount of possible applications for analog computers. Basically all fields where you need very high energy efficiency and or very high computational efficiency. I think the most financially interesting field will be artificial intelligence, basically implementing neural networks in analog electronic hardware. This might be spiking neurons. This might be just linear algebra using matrices of configurable resistors to perform the matrix operations. For example, medical applications, implants, brain-computer interfaces, high-performance computing, which is what interests me most. So solving very time and energy efficiently complex systems of ordinary or partial differential equations, industrial control systems, Monte Carlo simulations in the financial industry, really everywhere where energy efficiency and or computational power is of utmost importance.
Well, that's quite a range because artificial intelligence is such a popular subject these days. Maybe we can home in on that and sort of how could you envisage that this analog computing model can help in AI?
The easiest approach, and Daniel can, I'm sure, give some more interesting and in-depth examples. The easiest approach is you could just implement the intricate matrix operations that you currently do on graphics cards in an analog way. So you could set up a matrix with resistors and you feed currents, for example, into the column lines and perform automatically using Kirchhoff's law an addition of currents in the row lines. And voila, you have performed a matrix vector operation with basically no operation at all. You just let currents flow through a matrix of resistors. So that would be a very naive way to implement artificial neural networks on an analog computer.
Peter, if you look up here following my hand, you see a piece of a GPU cluster that I built using some GPUs I bought on the secondhand market. So we are already looking into that field, but I think going away more from the technological standpoint is also the question, why should you do AI on an analog device? And what's the benefit of doing this as low power, right? Because for whatever reason, companies build these big data centers nowadays, but this all requires you to have a constant internet connection. When you want to use AI, maybe sometimes you're on the go. Sometimes you want to use it offline. There's points, right, where you don't want to share your data that you enter into the AI, the big companies. And by going to lower power hardware for AI, one big opportunity is that you can use it on your device. So on your smartphone, on your laptop. That's not just text-based AI. It could also be AI that listens to your voice, right? Or records images and analyzes them. At this point in time, when you talk to your smartphone, it sends it into the cloud, gets it analyzed, comes back. There's a given latency. But if analog devices work on your device, it's instantaneous and it's private. No data is sent to the cloud. And also more energy efficient. I think it's becoming more and more important because the energy is expensive here. And so many data centers are gobbling it up. It's much better for all of us if we just do it locally and energy efficient. And it's also good for your smartphone battery.
Well, you might have to convince the CEOs of the big companies. Because, I think they're quite happy with the solutions they have. But let's home in on, we want to replace the GPU with, say, an analog model or analog computer for doing these kind of matrix calculations, as you just said. Do these devices actually exist, or do they need to be built? Or is there something on the way that could help make these kind of things a little bit more energy efficient?
There is already done quite some research on this topic. For example, IBM unveiled an analog LLM accelerator, I think 2 or 3 years ago, which basically performs the linear algebraic operations using matrices of phase change resistors. There's quite some work being done there, but there are also completely different approaches. For example, you could also abandon the idea of performing just linear algebra in the analog domain, and you could, for example, implement spiking neural networks with analog equivalents of spiking neurons, or you could implement oscillators using analog computing elements and have a neural network based on oscillators, which is currently a very hot topic in research. There are many approaches.
Daniel.
In the digital world, people these days always look at transformers, right? They are the new kid of the block have been for the last 5 years, and everything is optimized towards transformers. But then we are already seeing that, and I think many people have told us that in podcasts and in talks, that we are running out of data. So it's becoming more and more hard to build and to train these models. But the point is, these models always train from first principles. So they always need to derive everything from data. But we already know stuff. So for example, we know that analog computers build or execute physical models. So you could also think of the other way. Instead of running a whole neural network or a whole machine learning model on an analog computer, you could integrate the analog processor into the neural network, which would give the neural network the ability to reason and to learn with physics. So it already has a concept of physics built into the network. And that is interesting as well, because it could lead to more efficient networks that don't need to learn everything from first principles.
It might be interesting to dive a little bit deeper into that subject. It sounds almost philosophical, actually, because it's quite a different approach to computing is what we're saying. So there is the element of, yes, it can replace part of what we do now in the digital world with analog, but actually the analog computing opens up very different avenues of how to do things.
Definitely. The analog computer will not replace the digital computer, but it will complement the digital computer since it excels at certain types of problems, which the digital computer is just not made for it.
So talking about computers, you yourself have created one because there is the analog thing and the company behind it, Anabrid. Perhaps you can talk a little bit about what that is and what you hope to achieve with that.
Basically, the analog thing was not our first product and is not our only product. The company started in 2020, so we are now 5 years old. And prior to this, I built my own analog computer. I've been collecting analog computers for decades, but I decided it's time to build my own analog computer just to have a small-scale modern analog computer that I could carry around with me to lectures, show my students and the like. And when I unveiled this homebrew analog computer, I got a call from a university in France which wanted to buy some. And that basically got me thinking maybe I should gather some of my friends and start a company working in this field. And that was our so-called Model 1 analog computer, which has now been discontinued. And about a year later, we realized that we need to bring analog computing to the masses. That is much simpler with an analog computer than with a quantum computer. And we set out to build a small-scale analog computer that is capable enough of doing things that are not trivial. And that is what became the analog thing, or that for short. And of this device, we sold an incredible amount worldwide to hobbyists, to students, to universities, to industrial customers. And the analog thing still is a classic analog computer, since you have to program it by manually patching cables on central patch panel. But that's not our only product. It is purely meant for the educational market to bring the idea of computing with model-based approaches in contrast to our current algorithmic approaches back to students and pupils. We also already have reconfigurable analog computers. The smallest of these is the so-called Lucy Duck. That is, Daniel already mentioned the system. It has 8 integrators and 4 multipliers and 32 coefficients. And with 8 integrators and 4 multipliers, you can also do pretty interesting stuff ranging from applications in robotics or research in chaotic systems, something which interests me personally very much. And we also have a very, very large-scale reconfigurable analog computer. In fact, the largest reconfigurable analog computer ever built, the RADAC system, which we built for the DLR. And the RADAC eventually consists of 1,000 integrators, 500 multipliers, and 8,000 coefficients. So you can actually do things on the RADAC which are out of reach for a classic digital computer.
So, but the analog computers, let's start with a simple device, because that's what I looked at, the analog thing, where you have to connect things with wires. So how do you actually get the data out? Can you connect that to a digital computer?
Yes and no. The natural way of getting values out for an analog computer would be to use an oscilloscope. I personally would, of course, prefer an analog oscilloscope due to religious reasons, so to say. But nowadays you would use a cheap digital oscilloscope, which you can then use as a data logger and get the data from the digital oscilloscope.
Right.
Or you could use an Arduino, which you can connect with 6 or 7 wires to a so-called hybrid port at the back of the analog thing, which can then sample the values of up to 4 computing elements simultaneously during an analog computation run. So yes, you could either use an oscilloscope, a modern digital oscilloscope, or set up a little homebrew system using an Arduino or a Raspberry Pi or something like that.
How hard a battle is it, from your perspective, to convince people that analog computers actually are a thing, they're important, and there's a lot of them around, or there will be, and that we can train people to think differently about computing than what we've been done so far?
The first thing gets simpler day by day, since it becomes more obvious that digital computers are about to hit physical boundaries, especially with respect to integration density and energy consumption. As cool as it is to have a dedicated nuclear power plant next to your data center, it does not scale. So people are forced to look into different computational paradigms. And basically you have only two. You have quantum computing and you have analog computing. And both complement each other. Analog computers are ideally suited for problems quantum computers are not well suited for. So convincing people to take this into consideration is getting easier week by week, so to say. Getting people to think like this can be a problem. Daniel's work on the compiler helps to mitigate this. When you have someone trained in computer science, it's incredibly difficult because you are always confronted with questions, yes, but how do I do a for loop? And the answer is there's no concept like a for loop. There's no if in an analog computer. It's really difficult to get people from the computer science to think the way you have to think to program an analog computer. It's much simpler with mathematicians or physicists or the like. But with a compiler that offers basically a seamless integration into our current software environment, that gets much more simple. And that's the important thing about the compiler development Daniel does.
As I said in the beginning, my background is in GPU computing, and that, at least in the beginning, is also one kind of a hybrid computing architecture. I remember in the beginning, there was no decent software stack for programming GPUs. So the first thing that people did was realizing that when you use a GPU, it basically renders an image. It renders a 3D scene into a 2D image. Yeah. And they figured out, instead of rendering, if I just put in nonsense images that encode numbers, I can do matrix multiplication. So in, I think, 2003, we saw the first paper where people used GPUs to do maths instead of just rendering. And that was sort of the start of the GPU boom. And then it took almost 5 to 6 years before decent software was available. Yeah. But then more and more people started using them, and they realized, oops, it's actually quite different to program GPUs, because GPUs are these massively parallel processors. And yes, technically you can do ifs, technically you can do fors, but your GPU will be way, 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 way slower than your CPU. At some point, I gave a course about GPU programming, and there were so many students who, even after a number of lectures and exercises, did like malloc, so reserved memory on the GPU, and did if and else constructions on the GPU, and then wondered why the heck their GPU was so much slower than a Python program. We saw that people learned to think like GPUs over time. If you look into the last 5 to 6 years, you might remember the big jump on Apple devices they had when they went from Intel processors to their own processors. Yeah. I think these are called M processors, so M1 and 2. Interestingly, they're really good at doing local machine learning. And the reason for that is that they're not just a processor, they're what's called a system on chip. So there's a small part of the processor is a matrix multiplication engine. A small part of the processor does voice recognition and audio signal processing. And then you still have your CPU. But all of these devices interact. So I think people, and especially programmers, engineers, they've already been convinced that you need different computational paradigms to effectively execute your workload. Granted, analog is a way different paradigm than all of these devices. But people are already in the mindset, so they know they need, especially in the future, they will need to combine different architectures and completely different devices to solve their problems effectively. And analog is, I think, just one more piece of the puzzle then.
All right, so there is a sense of urgency, or people are waking up that there is a sense of urgency in terms of if we want to scale to bigger computing powers without actually having a nuclear power plant in our gardens. So,
Yeah,
in
I
order to
actually
go,
went to an AI conference here in Frankfurt yesterday and talked to
yeah.
some people. You know, there's this push to get AI, what's called gigafactories, into European Union. And just the sheer scale of these data centers is mind-boggling. Like there are now startups that procure 10,000 GPUs and now are trying to find a place in Frankfurt where there's enough power to even run them. I get where they come from, but it's just incredible.
Yeah.
I tried talking to them and they told me, yes, we are already hitting power walls and this is just the first of our planned deployments. And then they think about building small modular data centers in shipping containers so they can ship them wherever the energy is. That all might be a good idea, but at least I personally think that's not a solution we are looking for.
Okay.
I'm not saying analog is the solution, but it's definitely one part or one piece of the puzzle.
So there are different components that come together, and analog could be one of them, is what we're saying. So I want to move on in the last part to something that I'm seeing in the background with you, Bernd, because you're sitting what looks like a library and lots of equipment. I think you run an analog museum, don't you?
Yeah, that's right. I started collecting analog computers when I was in my teenage years, which was perfect timing since that was the time when classic analog computers were outphased from many industrial institutes or university institutes. And over the years, the collection became really large. I have analog computers dating back to the 50s. And analog computers from the 1980s, so I can demonstrate the whole range of analog computing development. I even have mechanical analog computer, at least parts, and most of my machines are also in working condition, so I can demonstrate it, or when there are visitors who are interested in actually programming classic analog computer, that is also not a problem.
Where do you store them? I mean, how do you find the room?
Basically, my house is filled with analog computers. It's just analog computers and a tiny bed for me. That's about it.
Okay. So the museum is at your house, basically.
Yeah, my house is a museum, so to speak. And we have pretty often visitors. Typically once a week or every 2 weeks, we have visitor groups ranging from 1 to 2 people and sometimes up to 16 people at once coming to visit the analog computer collection.
I'm sure they do. And it's near Frankfurt, is it? Or?
It's near Wiesbaden. From Frankfurt, it's about 60 kilometers next to Bad Schwalbach, which is a rather tiny village in the Taunus. And just send me a mail and make an appointment for a tour and come for a visit.
Next time I'm in Germany, I will certainly do that. And I think we also need to give the listeners a little bit of an opportunity to read up on that. And I think there are links available. There are certainly books available because you've written, I think, 2. Daniel, your work on the compiler, is that something that people can look up and follow, or?
Not right now. So we are currently working on a product which will be a add-on to the LucyDuck and to the Z, which is, well, basically it's a Raspberry Pi with our software stack that is connected to the machines, and it enables people to use the compiler and use the LucyDuck like we described.
Right.
But it's not out yet, but maybe we should prepare a paper, Bernd, on that subject.
Okay.
If anybody's interested, just feel free to just send us an email to AnnaBrit, reach out on LinkedIn, on whatever your favorite platform is, and we are happy to help. We are happy to discuss.
So what's in store now for the next year?
We had our second tape out. Tape out means when you finished your integrated circuit layout and gave it to a fab for fabrication. And this is already our first reconfigurable analog computer on chip. It's not very large scale at the moment due to financial and personal restrictions at the moment. But with this chip, we will be able to demonstrate that we can do high performance analog computing in modern CMOS technology in a fully reconfigurable way. And next year, we will ramp up our IC development capabilities substantially so that we will, I'm pretty sure, have a larger scale analog computer on chip for tape out ready next year.
Daniel, you're working on the same thing, or?
Yeah. And I think we should maybe take a step back here. because we never mentioned this when talking to you. But one part of the company is essentially building what's called discrete electronics. So that's the LucidDuck, that's the REDAC. So these are these analog computing devices. But then part of the company is also looking into miniaturizing the whole thing. For example, the biggest analog computer ever built, like Bernd said, the REDAC, is like one full 19-inch rack.
Right.
So it's like it's as tall as I am. But then we are looking to, in the next years, to miniaturize the same amount of compute onto one small integrated circuit. And then we hope to get it faster, so do even more compute on the chip and also be even more power efficient. That is what Bernd was referring to. And then coming back to the compiler, we already are working on supporting the next tape out in the compiler. In the coming weeks, at some point, we'll push that. And then that means you just define your model as an ODE or in different means in your favorite program language, and you hit compile. And the output could be for LucidDuck. It could be for a chip. It's basically just one flag that you switch.
But there's a lot of exciting stuff happening in the space of analog computing, and I look forward to seeing more of that. And I really do like to see the museum. Not quite sure when that will happen, but it sure will. And it would be great to see that. And you, of course, in person, not just online. So I thank you very much, all of you, for your time today, and all the best for analog computing, Anna Brid, and you personally.
Thank you very much.
Thanks for having us.
As both Daniel and Bernd just said, programming an analog computer requires a change in mindset, and in some ways, we need to unlearn some of the stuff we learned in computer science and engineering. In order to get to grips with this, they built a teaching device which you can get from their website at annabreed.com. And if you're interested in finding out more about analog computing and want to meet other experts in the field, there's a conference coming up later this year, the Analog Computing Days 2026, on the 11th and the 12th of June in Frankfurt in Germany. You find the links with all of that and more in the show notes as per usual. As I said at the beginning, there are lots of different types of computing devices apart from the ones we know and are familiar with. And later on this season, I want to talk about another one of those, the so-called Field Programmable Gate Array, or FPGA. It is not an analog computer, in fact it's digital, but programming for them is quite different from the way we develop applications for our standard computers. But first things first, next week is the last Tuesday in February, and so it's time for a German language episode. And this time I'll be talking to Katrin Schöning-Stierand from Hamburg, whom I met during a visit there last November. Katrin is very active in the research software engineering community in and around Hamburg, and I was interested in finding out what's been happening there. So for all German speakers and those who want to brush up their German language skills, I hope you'll tune in then. Thanks for listening. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya!